Hey guys, Mr. Backward here. In this video, we're going to look at one-sided derivatives. So as we're talking about one-sided derivatives, a function y equals f of x is differentiable on a closed interval from a to b if it has a derivative at every single interior point on the interval, and also if the limits, so the limit as f of b plus h minus f of b all over h, as h approaches 0 from the left-hand side, that's called the left-hand derivative at b, and also the limit of f of a plus h minus f of a all over h as h is approaching 0 from the right-hand side. That's called the right-hand derivative at a. Those limits also have to exist at the endpoints. So in this example, we're going to look at some one-sided derivatives, and what we're going to show is that the following piecewise defined function has left-hand and right-hand derivatives at x equals 0, but no actual derivative there. So the function we're working with is y equals x squared for x values that are less than or equal to 0, and 2x for x values that are greater than 0. And the first thing that we're going to look at doing is the left-hand derivative. So we're going to be looking at the limit of f of b plus h minus f of b all over h as h is approaching 0 from the left-hand side. Now the b value, the end point that we're looking at a b value of 0. So we're really looking at this limit of f of 0 plus h minus f of 0 all over h. And what we want to keep in mind for this first one is that we're approaching 0 from the left-hand side. So if you're approaching from the left-hand side, that means you're starting with values that are less than 0. So we're going to be focusing on this top piece of our function there, because x squared is defined for x values that are less than or equal to 0. So f of 0 plus h means in here for this x squared, we're going to plug in 0 plus h. So we're going to get 0 plus h squared minus f of 0 means we're just plugging 0 in. So we get 0 squared all over h. Well, 0 plus h is just h, and if you square h, then you just get h squared. And then subtracting 0 squared, well, 0 squared is 0, and if you take h squared and subtract 0 from it, it's still h squared. And then the denominator is just h. Now we're going to be able to do a little bit of canceling here. We've got h squared on top and just h on bottom. So we'll be able to cancel out this h on bottom with one of those h's on top. So we get just h. Now we're doing this limit as h is approaching 0 from the left-hand side. And since we're left with just h, if we direct substitute 0 in there, then we just get 0 as our answer. But now let's also look at our right-hand derivative. So here we're doing the limit of f of a plus h minus f of a all over h, and we're doing this limit as h is approaching 0 from the right-hand side. So just like we did on the previous one, we did a b value of 0. Here we're going to be using an a value of 0, since that's the x value that we're taking a look at. So this is going to be f of 0 plus h minus f of 0 all over h. But now we're doing this limit as we approach 0 from the right-hand side. So we're starting with numbers that are bigger than 0. So the function 2x is defined when your x values are bigger than 0. So f of 0 plus h means we're going to be taking 2 times 0 plus h minus 2 times 0 all over h. Well, 0 plus h is just h, and 2 times h gives me 2h. And then on the back end, 2 times 0 is 0. So if we take 2h and subtract 0 from it, then we've just got 2h. And this is all over h. Notice those h's on top and on bottom cancel each other out, so we're left with just 2. But we still need to do this limit as h is approaching 0 from the right-hand side. When you take the limit of a constant, the answer is just the constant, so we just get 2 here. So the left-hand derivative, we came up with 0 as our answer. The right-hand derivative, we came up with 2 as our answer. So individually, the left-hand derivative exists, and it's 0. And the right-hand derivative also exists, it's 2. But since we have different derivative values on the left side and on the right side, the derivative of the entire function at an x value of 0 does not exist. That's going to be it for this video. Thanks for watching.